Hello and welcome to our second lesson on vectors, where now that you're familiar with what vectors are, we're going to be looking at vector operations. Specifically, we're going to do vector addition, subtraction, scalar multiplication, and today we're working with geometric vectors and in the two dimensions. And then we're going to expand this next lesson to then algebraic vectors. So just to start off with an application-based question, we see where vectors can be used. Consider a ship that's being pulled by two tugboats as shown below. So here we have our ship and we have two tugboats that are moving this ship. And often when ships are docking, this does happen where the tugboats guide them to where they're supposed to go. So let F1 be the force exerted by the first tugboat, so this one, and F2 be the force exerted by the second tugboat. And we can see they are both going in different directions. So theta is going to be the angle between the two forces of the two tugboats. So first, let's have some observations about what this means. So as we can see, the direction of the forces from each tugboat is shown with the arrow. So this one is going towards the right or the east. This one is more going towards northeast, but closer to the east. So the magnitude of these forces, so how much they're pulling the ship by, is the length of the force vector. And we can see this one is the length of it is greater than the second one. So this one the first tugboat has a greater force than the first one, or the second one, sorry. And so yes, longer force vectors indicate a greater exerted force. So the longer the vector, the more the force. Now, as these tugboats are pulling the ship, they're both attached at a common point, and that's why we see their tails are both at this point. So they have a common tail or a common endpoint. As these two tugboats are pulling this ship, we expect the ship to sort of go into a movement which is going to be approximately in the middle of the two tugboats as they are pulling it in these two different directions. And the combined magnitude of the forces will actually be not the two forces added together because of the difference in direction. So if we had both of the ships, both of the tugboats were in towards the east, which is harder to manage because they might like crash into each other. But if we had that they were both pulling from the east, then we could say the combined magnitude would be the addition of the magnitude of each of the tugboats. However, in this case, they have different directions, so we cannot just add them. That being said, we know that the combined magnitude will be greater than F1 and it'll be greater than F2 because you have two different forces pulling, but it's not going to be exactly the sum of the magnitude of F1 plus the magnitude of F2. And we also can conclude that the ship is pulled in a constant direction with a certain force. So these two these two force vectors together will ultimately end up, for example, as one vector that's going perhaps in this direction with a specific magnitude. So we can make a conclusion about the resulting force from both of these tugboats. So, how can we find the vector that shows the combined magnitude and the direction in which the cargo ship is being pulled at? So, again, it's not necessarily right in the middle, and it's not necessarily the sum. The magnitude is not the sum of the two magnitudes. We do have to take into account the magnitude of each force as well as the angle that they are pulling the cargo ship at. But how can we find this combined vector, which encompasses all of that? And that vector is actually called our resultant vector. So a resultant vector is the sum of two vectors, and it represents the combined effect of the two forces, both in regards to magnitude and in regards to direction. So if we have F1 and F2, and you can now consider these two to be the two tugboats here, if we have the same tail for them, and theta is the angle in between, then we can form a parallelogram. So this one is actually F1 and this is F2, okay? Because that's how a parallelogram works. And so the resultant R, which is the addition of these two forces, is going to be the diagonal of this parallelogram, both in direction and in terms of the magnitude. So depending on this angle, if you have a smaller angle or greater angle, you will see that the diagonal will also be different. It might go a little higher, it might go a little lower, which determines the direction. And if F2 is, for example, longer, then we're going to see that R will also be longer, so it will affect the magnitude as well. And so today's class, we're going to see how to find what this R is, again, both with respect to direction and its magnitude. And it is our parallelogram law for adding two vectors. So given two vectors A and B, so A is also AC because of its endpoints, and B is also AB because of its endpoints. And we want to add these two forces or vectors together. Then we place them tail to tail, so they have to share that common endpoint there. And we form the parallelogram from these two vectors. So again, remember, this is going to be B, this is going to be A. So the two side lengths that are opposite each other are going to be the same. And the sum of these resulting vectors, and call it now AD, is the diagonal of the parallelogram. So vector A plus vector B, which is also vector AC plus vector AB, is equal to vector AD, and this is vector AD, and that's also the other notation for it. Now, consider a triangle that is formed here. So based on triangle properties, we know that A plus B, the magnitude here of this vector, which is also the side length of the triangle, is less than this side length plus this side length, which is also the magnitude of A plus the magnitude of B. And that's exactly what we were saying up here with the tugboats, that the combined magnitude of the forces will be greater than F1 or F2, but it's not exactly the sum. And so we see that based on triangle properties right over here. Now, we do have a special case as well. Again, like I was saying, if the tugboats were going in the same direction, or if they were also going in opposite directions. So think of, for example, a tug of war with a rope where you're pulling on opposite directions. Then if they're in the same direction, we do actually say that the magnitude of the resultant force is the magnitude of the two forces or the vectors added together. So if you, for example, have one that's going, and these are both going east, this one, it has a magnitude of, let's say this is V, and V is 2. And then you also have another one that's going like this, and this is U, and we know that U is perhaps 4. Then U plus V is going to be 6 because they're going in the same direction. And in this case, what's really happening is if you combine that force and put U here, then this total is 2 plus 4, and it's 6. So that's where we get that 6 from. Now, another case is when you have opposite direction. So think of that tug of war. If you are pulling from one side and your force is 10, and someone else is pulling in the opposite direction and they're pulling at a force of, let's say, their force has a magnitude of 6, then the resultant force there is going to be one force subtracted from the other force, the magnitudes. So mine, which is 10, would be we would do 10 subtract 6, so it would be 4 in my direction. So consider this, this is the middle point of the tug of war. So you have one force going this way, So let's say this is U and it has a magnitude of 10. And then you have another one that's going in the opposite direction, and this one is V and it is 6. So then the resultant of these two is going to be 4 in the right direction or towards the east because this is the greater force there. So you just subtract their magnitudes and the direction will be of the one with the greater magnitude. Now, this is again special cases. We don't always have that they're going in the same or opposite direction. So when they're not going in, when they're going in different directions, we go back to our parallelogram. Um, so in this case, also don't mind, I know this part is not the straightest. It should be a straight line, um, but it looks a little bit off, but it is a straight line. So here we are given vectors A and B, and here A has a magnitude of 2, and B has a magnitude of 3. And, oh, and this also should be, there we go. The angle between A and B is 60 degrees. So not just the part, the beginning part, so it should be for both. In between vector A and B, this is 60 degrees. And we're asked to find the resultant. So forming our parallelogram, this is our resultant force, which is also the diagonal of the parallelogram. Now, here you have to think of this as a triangle where we are using cosine law here. So A plus B, and this is just from cosine law, which is given to you here. A plus B, the magnitude squared, is going to be equal to the magnitude of A squared plus the magnitude of B squared, because remember, this is also now B, or it's actually just B, and then this is A. So you can either think of it as this triangle or this triangle, doesn't matter. And if you take away 2 times the magnitude of A times the magnitude of B, and then cosine of OBC. So so I guess this one we were looking at, OBC, and we're looking at this angle here. But based on properties of a parallelogram, we know that this is also 60 degrees. So then these two, and you're also thinking, you can also think of it as straight line properties, right? If we have this as 60, then this one is 120 degrees, and so this is also 120 degrees. So really, we have the magnitudes, we have this angle, and all we're solving for is the magnitude of the resultant. And that's exactly what you see here. So A, the magnitude is 2, 2 squared, and then B, the magnitude is 3, 3 squared, minus 2, and this is the magnitude of A, magnitude of B, and then cosine of 120 degrees, which is this angle right here. And again, you can think of it as this one too. It would have just been angle OAC, which is the same. And now just solving this through, and this one was an easy angle, so the cosine is just negative half. Then we are given that the magnitude of A plus B squared is 19. So then taking the square root, and we do have to have a positive value here for the magnitude. So A plus B is going to be just the positive square root of 19, which is approximately 4.36. So here I have shown you this with the parallelogram, but I hope you can see now that we can actually solve this, and there is another law for it, which is called the triangle law of addition. And I want you to think, again, based on just the fact that we use the triangle here, but specifically which triangle, how can we use that to add vectors? So in um, the triangle law, so this is, I'm just going to show you here. We start with vector A, and now vector B, instead of starting with the same tail as A, it's going to start from the head. So there. And I'm for now just trying to follow this A and this B approximately. And maybe this one should be a bit smaller because the magnitude of B is greater. And now I am just going to draw this vector from A to the head of B, which is going to be A plus B. And you can see this is actually just the half of the parallelogram, but then we're just taking away that step of completing the full parallelogram. And the distinction here would also be you kind of have to picture that the angle that you're given is between A and B. It's not necessarily here. So this one will stay 120 degrees, and it's because if you have B back here, if you have them as tail to tail, which is that they share a tail, that's what that 60 degrees is telling us when it says the angle between them is 60 degrees. Not necessarily here. So, and I'm sure you can see that that's greater than, is an obtuse angle. It cannot be 60 degrees anyways. But if we had here extended, then this would be 60 degrees. And again, this is the idea of if A was moved up here, then you have that tail to tail. So that's pretty much the difference between parallelogram law and the triangle law. In the parallelogram law, you have tail to tail, but in this one, you have head to tail, which means that from the head of the first vector, which is A, you draw the second vector starting at its tail. So we have head to tail of B, head of A to tail of B here. And again, the resultant will just be the from the starting point to the final ending point, which is vector B here. So not necessarily here because that's just vector A, but these two will be the same. So see which one you're comfortable with using. I just find the parallelogram is a little bit visually, or visually it has more to it, especially when teaching it. It helps to start with the parallelogram, but sometimes you'll see me use the triangle law as well in later lessons, but the result will still be the same. Now, we're also, and we've seen this before with opposite vectors, but now we're just giving it a definition now that we have learned vector addition. So we have now a zero vector. So when two opposite vectors are added, we do have that the resultant or their sum is the zero vector. So again, here it doesn't matter what A, B is, but any random A and B that you choose, and the vector in between them, so this one is AB, then the opposite vector is just going to be starting from B, now going towards A. Oh, and this is BA. So what's important about them is they have the same magnitude, but their directions are opposite. And that's exactly what we're getting from the opposite direction case here, because you will have AB, for example, is M. And BA, the magnitude will also be M. So then the resultant will have a magnitude of M minus M, which is 0. And we do say, because we're working with vectors, we don't just put 0 because a vector plus a vector should give us a vector. So then we say we have this 0 vector concept here. And you will see the 0 vector used in other contexts as well, but that's pretty much what it means. Now, we also see subtracting vectors, and it's pretty much when you're subtracting vectors, you're adding the opposite of the vector that's being subtracted. So we're just turning it into vector addition, but so we have, for example, vector A minus vector B. We're going to start with vector A, and now we're going to make a vector B its opposite vector, which is just negative B, and we're going to add that. So then we can still hold the same rule. So here, And now I'm showing you the triangle law here. This is vector B. So then the opposite vector will be starting from the head going towards the tail. So this is negative B. And that's exactly what we are seeing here. We start with A, but instead of going B on this side, because we're subtracting, we're going in the opposite direction. So this is, this should actually be negative B there. And this, now the resultant, which is from the starting point to our end point here, is A minus B. And you would do the same process with the angles to whether you have, depending on which angle you're given, you can do sine law, cosine law to determine the magnitude of A minus B. Now let's try to solve an application question here. So an airplane heading south at a speed of 300 kilometers per hour is met with a wind gust blowing from the west at 100 kilometers per hour. So starting with this part just here, I want to specify that speed is 300 kilometers per hour, but now that we have heading south, giving it that direction, this whole thing together is a velocity because it has a magnitude, and this part is scalar, but with this direction now, it is a vector. And same with the wind, it has a direction and a speed, so it is a vector. And we're asked, what is the resultant velocity of the airplane relative to the ground? So pretty much this wind is acting on the airplane and it's making it move, giving it a change of direction and possibly also affecting its speed. So we want to now know what the resultant velocity is. And this resultant velocity is going to be telling us what is the new direction that the plane is moving in, and also at what speed, based on the effect that the wind has on it. So let's start with defining our variables here and then drawing a diagram. So V, we're going to let be the velocity of the plane. W is going to be the velocity of the wind. And R is now the speed, or actually I'm going to change this probably for you to velocity of the airplane as the wind exerts force on it. So what is this new velocity or the resultant velocity? So again, this is resultant. Now in our diagram, we have the plane moving south, and then we have wind that is blowing from the west, so from the west, not towards the west. So if it's blowing from the west, it's going towards the east. And it is 100 kilometers per hour. So this is not drawn to scale, but approximately this is 1/3 of the velocity of the plane. And that's because this is 300, this is 100. So this is our plane and now the wind, and this is now our triangle method. And now keep in mind, because this was south and this is going east, this is actually a right triangle here. And so our resultant force is V plus W, which is R. So here, the magnitude of R is going to be the same as V plus W squared. And this is from Pythagorean theorem, where we get V, the magnitude of V squared plus the magnitude of W squared. So this side plus this side squared, or this side squared plus this side squared is the hypotenuse squared. So R is going to be the square root of 300 squared plus 100 squared, and this is approximately 316 plus, 316.23, and this is kilometers per hour. And so we actually see that the plane is now speeding up. It's going at a greater speed, or a greater, well, speed for now because we haven't added direction in. So this actually means the wind is pushing it and it's moving even faster than what it was, which was 300 kilometers per hour. So to find the, this should be to find the resulting vector, because we already have the magnitude. We also need to find the angle, which tells us the direction. So we're essentially trying to find this angle here. So we say the tangent of theta is going to be the magnitude of W over the magnitude of B. So remember, SOHCAHTOA, TOA is opposite over adjacent, so the opposite over adjacent here. And I suggest using this over sine or cosine. First, because this one is it's a decimal, so it's not an exact value. But also, in case you made an error here, you're not using your error to solve for the second part, which might give you another error. You're using the given values, which decreases the chance of error here for you. So here we have 100 over 300, which is 1 over 3. And so theta is the inverse tangent of 1 over 3, which gives us approximately 18.4 degrees, and it's going southeast. So writing this, and we start with south, which is this line here, and we're going 18.4 towards the east. So the airplane is traveling as 18.4 degrees east at a speed of 316.23 kilometers per hour. And again, keep in mind, this part is speed because it doesn't have the direction, but this combined is our velocity. And don't forget your units as well. Now we're going to see scalar multiplication. So scalar, remember, is just your numbers with no direction. And now we're going to multiply that by vectors. So given the vector k, a, so here, and maybe I'm going to fix this for you, but it should be like this. Because really the vector is over a and not on k. So k is a scalar and a is a non-zero vector. If k is greater than 0, then k times a is in the same direction as a, and it has a magnitude. And again, k doesn't go in the magnitude part because it's a scalar, but it's k times the magnitude of a. So if we have k between 0 and 1 in the same, and it's going in the same direction, then the vector is shortened because you're saying whatever direction you were going in, just take a portion of that, which is between 0 and 1. So think of your fractions. But if k is greater than 1, then the vector is lengthened. So starting with a here, we can see in this case it's shortened, and in this case it is lengthened. Now, if k is less than 0, then we say that it's going in the opposite direction as a. And its magnitude here. And see here, I do have the absolute value because I already know that I'm going in the opposite direction. So with regards to the magnitude, it doesn't make sense to say the negative because the negative is impacting the direction and not the magnitude. So for the magnitude, we do have the absolute value of k times the magnitude of a. So now, starting with a here, and see how these two vectors, which are the resulting vectors, are going in the opposite direction. So if k is between 0 and -1, then again, we're shortening the vector. And if k is less than -1, then the vector is lengthened. This can also be interpreted as if the magnitude of k, or sorry, the absolute value of k is between 0 and 1. And in this case, if the absolute value of k is greater than 1. Also, if k is 0, then the resulting vector is just the 0 vector. If k is 1, then the resulting vector is just itself, the original vector we started with, so just a. And if k is -1, the resulting vector is the opposite vector to a, so it's just the opposite vector. Now we also have the concept of collinear and parallel vectors. So two vectors u and v are said to be collinear or parallel if and only if there exists a non-zero scalar k such that vector u is equal to k times vector v. So pretty much it is a multiple of the other vector. And keep in mind it's non-zero because if it's 0, then multiplying it is just going to give you the 0 vector, so it's going to be true in all cases. So that's why we need to have non-zero scalar. And for example, this could be Um, if we have 2, 3, and we will see this later when we do algebraic vectors, but if you have u is 2, 3, and um, we have k v is 4, 6, then we know that k is, this is pretty much like double or 2 times u, so then these two are collinear or parallel vectors. So now let's see properties of vector addition and scalar multiplication. So we've seen how they work, but now these are all of the properties. And it will be for vectors. It does work differently than integers in some cases, or integers and real numbers in some of the cases. So we do still have the commutative property, which means that a plus b is the same as b plus a. We also have the associative property, which means that a plus b plus c is the same as if you first evaluate a plus b and then add c, or if you first add b plus c and then add a to the resulting vector of that. With scalars, we also have a distributive property. So if you have k times the vectors a plus b added together, then the scalar multiplication can be distributed. So we have k times vector a plus k times vector b, given that k is a real number. And now adding the zero vector, this is similar to if you're just adding zero, it doesn't change your vector. So a vector a plus the zero vector is just the vector a. Now for scalars, we also have the associative law, which means that if you have two scalars m and n in real numbers, then m times n a is the same as mn times a, or you can take the brackets out, mn times a, as long as you know m and n are your scalars. We also have the distributive law for scalars. So if you have those two scalars added together, m plus n, in this case, times the vector a, then you can actually have the scalar m times a plus n times a, and this will be the same. So we're going to see a few examples now. So we're asked to simplify this expression. So we're going to be using a lot of those different laws here. So first, starting with our distributing our scalar into this bracket over here. So here I've just rewritten it, but here we distribute it. So 4 times 3, we have 12a plus 4b plus 8c. And then in this case, we're just distributing the negative. So it becomes negative 2a, negative 3b plus c because it was a negative here. Now, this is the part I was mentioning above. Make sure your scalar does not have that arrow on top. The arrow only belongs to the vector. So you can see it better here now where the arrows are just above the letters because the scalars are separate from the vectors. And now I'm just combining, I had 12a minus 2a, which gives me 10a. I had 4b minus 3b, which just gives me b. And 8c plus c, which gives me 9c. And that's it. I'm done. That's my simplified expression. Now, here we're asked, or we're told, x is 3p minus 4q plus r, y is q minus 5r, and z is minus p minus q plus 4r. And we're asked to find each of these in terms of p, q, and r. So starting with this first one, x plus y. So first I'm just going to write 3p minus 4q plus r, and then I'm going to add y here, so q minus 5r. And I don't have to distribute anything here, so this will just be 3p minus 3q minus 4r. Now, in this part, starting with, I'm going to start with my x. I do have to account for when I am subtracting z here, I'll have the bracket. So then when I'm distributing it, I do have to distribute out that negative, which will give me plus p plus q and minus 4r. And now this will give me 4p minus 3q and then minus 3r. And for example, if you did have all of these as 3, you could have one extra step at the end to factor out that 3 and write it as P minus Q minus R. Um, so you can do the opposite way as well, where you can factor out, but not the case here. And I'll let you try C on your own here. Just again, pay attention. You do have two scalars here, so you do have to distribute that out. Um, Maybe I'll just take a moment and I'll give you the answer, but try it on your own. Okay, so a little short on space, but this one is just x. This is minus 2y, and this is 3z. So now I'm just combining all of these, so this is just continued from there. So gather all of my p's. So we see these ones are just the 0 vector, so not necessary to write it. For q's, I am left with negative 9q. And then for r, we have 23r. And that's the final answer. And that's actually also our last example. So I actually think vector operations are really fun. So I hope you enjoyed them as well. So some practice questions here for you as well. Please make sure you're completing those. And as always, check Google Classroom for any additional tasks and any optional tasks that could help with the visualization or adding more knowledge to your understanding. And that is it. And don't hesitate to reach out if you have any questions, and I will see you all next class.